While the last few people are filtering in and finishing their breakthrough discussions, I'm going to just start the next session so we don't get too far behind. I'm delighted to introduce Paul Nathan, who's got a very interesting biography. 25 years in finance, and then finally saw the light and came back. And is now a PhD student at my alma mater at University College London. Has apparently written several novels, which is kind of cool. His talk, if you read the abstract, it's got a lot of sci-fi sounding terms like dimensionality and manifolds, but I think it's going to be really interesting and very foundational, and I think by the end of it you're going to have a really pretty good idea of the kind of concepts that we've been trying to convey with anomaly detection. So please, Paul, take it away.
Thank you very much. Perfect. Hopefully you can hear me okay. Thanks so much, Michelle, and it's great to be here. And thanks also to the amazing speakers this morning, especially Ashley, who I think has managed to lay down a good common vocabulary for a lot of the stuff that we do in anomaly detection. Welcome to my talk, Finding Pegasus. Now, with a room full of astronomers, you'd probably be forgiven for thinking that this is going to be a talk about this wonderful constellation, but actually it's about this little guy here. So what a winged horse has to do with science and discovery, and how Pegasus is kind of helping me personally try to enhance unsupervised anomaly detection. Well, hopefully that will become clear in the next 15 minutes. My name is Paul Nathan, as Michelle said, and I'm from University College London's Centre for Data Intensive Science, where we're using AI and machine learning to try and answer some of the big questions in astronomy and also in particle physics. Like a lot of the speakers this morning, I'm an anomaly hunter, so I'm scouring the universe for the unusual, trying to understand it better, and also trying to find perhaps that elusive something that might push forward the boundaries of science. Now, to do that, the haystack of data that I'm sort of trawling through are astronomical spectra. So for those who are not quite so familiar with astronomical spectra, they're snapshots of light from distant objects like stars, quasars, and galaxies. And the light is split into its constituent colors, and those colors are characteristic of the underlying astrophysics and astrochemistry of the object being observed. It also holds sort of really important information about the object's distance from us and also their age. Now, I'm lucky enough to be part of a collaboration, an international collaboration called DESI, or the Dark Energy Spectroscopic Instrument, and already halfway through its initial sort of 5-year term, it's been starting to answer some of the sort of big questions around the universe's structure, history, and also its future. It's being run out of the Kitt Peak National Observatory in Arizona, and its mission is to gather 40 million of these astronomical spectra. And although that's still like an order of magnitude below some of the things that Michelle was talking about before, it's an order of magnitude above what we've got in terms of astronomical spectra at the moment. So I've got this big haystack of astronomical spectra to look through. That's my role, I guess, within the collaboration, to try and look through for the weird spectra. And the tool that I'm going to be using to try and identify these spectra is unsupervised anomaly detection. Now, again, we've had a good intro to this already, so all I'll say is that the unsupervised bit means that we don't have to label the data first. And so that's an extraordinarily powerful way of dealing with data, because it means we can let the machine learning algorithm or the computer essentially find structure on its own within the data set. And the anomaly detection is kind of as it sounds. I'm looking for weird stuff. I'm looking for sort of unusual things, isolated things, outliers. So they may be rare objects, they may be predicted phenomena, or they may be those elusive unknown unknowns that, say, Dame Jocelyn found in her work. The anomaly detection, we've already seen a couple of examples on the screen. So in 2 dimensions, and possibly even 3 dimensions, it sort of doesn't look too hard, right? You're looking for these outlier points, and it's relatively easy to see visually where those are. The problem is that we're not usually working these days in 2 or 3 dimensions. Again, as been sort of mentioned before, we're actually working in much higher dimensionality than that. So these are some examples of some DESI spectra from the Dark Energy Spectroscopic Instrument. These are all captured in 7,800 different wavelength intervals. So essentially, this data is 7,800 dimensions. And so the problem is that the tool that I'm using, unsupervised anomaly detection, doesn't really handle high dimension that well. There was a very nice paper recently, relatively recently, by Han et al., who looked at a bunch of widely used anomaly detection or outlier detection techniques, of which a good chunk of them were unsupervised. And they found that none of them, first of all, was statistically better than the others when they tested them across a whole bunch of different data sets, which is kind of what you'd expect from something called the no free lunch theorem in machine learning. But also, crucially, none of them performed particularly well with high-dimensional data. So why is high-dimensional data even a problem? Well, the raw data representation is often high D because of how the data is collected rather than reflecting any underlying physics. So I've already said, like, DESI spectra in like sort of 7,800 wavelength bins, so 7,800 dimensions, but images of galaxies are often much more higher dimension than that, maybe captured in tens of thousands or even millions of pixels. And this unusual, unnatural, high-dimensional representation lends us no physical intuition. It's hard or impossible to work with computationally, and means we're afflicted by what's called the curse of dimensionality. In high dimension, data becomes sparse as distance between the points increases, and points are found increasingly towards the boundary of the space. And weirdly, the distribution of those points becomes much more tightly spread. So the concept of nearest neighbors, which is fundamental to many anomaly detection techniques, starts to fall apart. So dimensionality reduction should be beneficial, and Ashley talked about that as well. But how do we do it, and is it actually a meaningful thing to do? Well, dimensionality reduction relies on something called the manifold hypothesis, and I appreciate it's still before 11 o'clock, and I was told once, but I should never mention manifold before 11 o'clock, but here we go. It's the manifold hypothesis that most real-world, high-dimensional data sets actually reside to a much closer, lower-dimensional manifold. We can just think, for the purpose of this, as a manifold as just being like a lower-dimensional surface. Now, that actually seems to be quite valid for astronomical spectra, which is my domain. There's some very good research by Yip and Portillo et al., who showed that you could compress astronomical spectra down from their 7,800 native dimensionality down to, say, 6 dimensions or 10 dimensions. And the reason that works so well is that actually the data contained in those spectra is very highly correlated. So that's great. So we can do it. How do we do it? Well, we can find that low dimension manifold, and again, we touched on a couple of these points already, using a linear projection method, using something called principal component analysis, which probably a lot of you are familiar with already, or a nonlinear manifold learning method, something like TSNE, or we could use UMAP, which again, we've seen already today, and some other methods, maybe a deep learning method like an autoencoder, which Ashley talked about. But the manifold we find will be different depending on the model we use, and that's a very kind of key point. Linear methods will find a hyperplane or a combination of hyperplanes. Nonlinear methods can find more complex shaped manifolds. So that kind of got us thinking, well, maybe we could reframe the anomaly detection problem from the perspective of this manifold. All right, so how would this work? Okay, well, there are two main ways of identifying outliers anyway, right? So one, and again, luckily we've already talked about this, is to look for points which are isolated or extreme in the distribution because of their distance from neighboring points, or because they're in areas of relative underdensity of points. And in high dimensionality, we've already seen that, it's problematic, so we usually transform to a lower dimension, and we look for extreme and isolated points on the low D manifold itself. So an example of a technique that does that is local outlier factor. Now we're going to call those points and those techniques on manifold. And then the other way is to construct a low dimensional manifold, which well represents the bulk of the data set, and then points which are far from this representation are assumed to be outliers. So that could be using PCA or autoencoder reconstruction loss, and probably not very originally, we're going to call those techniques or anomalies off manifold. All right, so all very well. Okay, the manifold is model dependent, we've already said that, therefore the anomalies detected will also be model dependent. And this is a key point. For a given manifold, on-manifold and off-manifold anomalies are going to be complementary, okay? And they're likely to be quite different. So this thinking would apply if we explicitly combine complementary on and off manifold methods, we're likely to consistently discover more anomalies. And the other thing is, if we've constructed the manifold well, then the on-manifold outliers ought to represent extremes in our current thinking, and the off-manifold outliers ought to be where we find new and rare physics. All right, so all very well, and all, let's face it, a little bit nerdy and theoretical. We're doing anomaly detection, so I want to show you some real data, but my real data is 7,800 dimensions. I don't think we're quite ready for that yet, so that will come in about sort of 3 or 4 minutes. But first off, I've devised a little illustration which takes a 3-dimensional data set and then compresses it down to 2. And we actually start in 2 dimensions. And I think that's hopefully will be a little bit memorable, and we can go with that. We're going to start in 2 dimensions, and our data set for, again, a room full of astronomers is horses, okay? I quite like horses, so, and we're going to plot height and weight of horses. So this is an idealized set of horse data. We'd expect it to look something like this if we plotted height and weight. There's reasonable correlation between height and weight for horses, right? But we're doing anomaly detection. We need some anomalies. We need some outliers. So we can have these 2 points here. So enter my 2 friends. On the left is Eohippus, which was a horse precursor. It was about 20 centimeters high. And on the right is a visualization of Samson, who was 2.2 meters high to the shoulder and apparently the largest horse that ever lived. I think that's still a slightly exaggerated picture, but you kind of get the idea. All right, so that's our horse data set, 2 dimensions. But we want to add 3, okay? We're not going to hold back. We're going to add 3. And this, our 3rd dimension that we're going to add is numbers of pairs of wings. Okay, most of the data here is going to be unaffected by that, as you'd probably expect. But we're going to have 1 point, and that point is, of course, going to be Pegasus, right? Pegasus flies to the rescue, right? Okay, so now we've got a 3-dimensional data set. Remember, we're doing anomaly detection. Okay, but we're going to pretend that we can't cope with 3 dimensions. So normally we're in something like 7,800 dimensions. We need to squish it down to maybe 6. We're in 3. We're saying we can't deal with that. So we're going to do some dimensionality reduction. We're going to use PCA to find a lower dimensional manifold. Now, the lower dimensional manifold that PCA is going to find is pretty much just going to be this height-weight plane. PCA works by finding essentially the plane or the hyperplane which best fits the data. Here, it's clearly going to be this, right? It fits most of the data very well. Okay, now we're going to project our points onto that lower dimensional manifold. Let me just take it one back. Most of these points are already sitting pretty much on the manifold. Pegasus gets projected down there into the middle. Now, this is a sort of an important point. Pegasus is average height, average weight, and its wings don't weigh anything because its wings are magical, right? I mean, it's not going to weigh anything, right? But I guess the important thing is there that if this feature that we're modeling with this extra dimension isn't well correlated with the other features, the observable features, the normally observable features, then it could be that when we do dimensionality reduction, interesting points can get lost in the middle of other points. All right, okay. Let's do some anomaly detection, right? So first of all, we're going to do on-manifold anomaly detection. We're going to use local outlier factor, right? Hopefully we know how this works now. We're going to look for points which are in areas of underdensity or isolated points. So we're going to find Eohippus, we're going to find Samson really easily, right? Because they're out on their own. But we're not going to find Samson, we're not going to find Pegasus, because Pegasus is lost in the middle of the other dimension. So local outlier factor will find us a couple of like extreme points, but it won't find us Pegasus. Now, if we used our other method, which is off-manifold anomaly detection, here we're using reconstruction error. So we're looking for points which are poorly reconstructed or poorly represented by the low-dimensional plane. Clearly, we'll find Pegasus, because it's very poorly represented by the two-dimensional plane. But we probably won't find Eohippus and Samson, because they're actually sitting on that plane. So if we sort of summarize, we can see we've got some on-manifold anomalies, we've got some off-manifold anomalies for this manifold, right? If we'd created a different manifold, we might have a different representation, but for this manifold, this is what we're seeing. If we could combine both of those sets of anomalies, we'll end up with a superset of anomalies which might help us to find all 3 of these anomalies. And they're all interesting points, right? We'd be interested in finding all these points. All right, okay. So that's 2 or 3 dimensions, right? We're going to get a little bit hairy now. We're going to go up to 7,800 dimensions. Okay, so this is using real DESI data. It's just a sort of, like, I guess, a toy data set, about 50 to 60,000 spectra, split 60% stars, 40% galaxies. What I've done is I've taken the raw dimensionality, 7,800 dimensionality. I've squished that down to 6 dimensions using PCA and an autoencoder, so I've done it in 2 different ways. And then I've visualized those 6 dimensions, because we can't really see 6 dimensions, right? So we still have to squish those down further into 2 dimensions using this manifold learning technique, TSNE, but we could have used UMAP or whatever. All right, now this is what these manifolds look like when we squish them down in 2 dimensions. So the first thing to note, which is maybe an obvious point, is that they look a bit different, right? And this makes the point that the manifold that we generate is going to be model dependent. The second thing and it's not just a rotational thing, they are actually a bit different. Second thing to note, maybe just in sort of like parentheses, is that you can see that the stars, which are in red, and the blue, and the galaxies, which are in blue, are kind of sort of separated within the distribution. And that's why, that's the other reason why people like unsupervised dimensionality reduction, because it gives you a bit of classification for free. All right, we're doing anomaly detection. So now we're going to take one of those manifolds, we can take the PCA manifold, and we are going to look for anomalies both on and off that manifold. We're going to identify, for the purposes of this, it's just a toy example, we're going to identify outliers as just like the 1% of points which are like most poorly reconstructed using PCA or which have the highest local outlier factor rating. Right, so first of all, this time we're going to start off manifold using our PCA reconstruction loss. So these are like our Pegasus points. So the bright blue dots on there are the points which, using PCA reconstruction loss, we identify as the most anomalous points. If we look on manifold, using local outlier factor, so for these are the points which are the most in the areas of lowest density and which are the most isolated points, we find these yellow points. So the sort of the obvious thing, the punchline of this is that they're not the same. Okay? The similarity score between these is only a couple of %. So if we combine both sets of anomalies, so a complementary on and off manifold method, we'll end up with a superset of anomalies, which gives us more potential interesting things to look at. And we see exactly the same thing with a different manifold which we've constructed from the autoencoder. Again, the on-manifold anomalies and the off-manifold anomalies are different. If we combine them, we get a bigger superset. Now, this is obviously only a starting point. Once you've got this superset of anomalies, you need something like maybe Astronomaly, that Michelle and Bruce worked on to curate those anomalies and actually then end up eventually getting an expert in the loop to visually inspect them. But what it does do is it gives you a bigger set of anomalies and of potential sort of weirdos that you can look for. All right, so quick summary and takeaways. Unsupervised anomaly detection can struggle with high-dimensional data. Hence, researchers usually choose to work in a lower dimension, and this creates a manifold which is model-dependent, hence the anomalies detected will also be model-dependent. And we've reframed the problem from the perspective of this manifold, dividing unsupervised anomaly detection techniques anomalies into on and off manifolds. For a given manifold, combining complementary on and off manifold techniques should widen the number of anomalies that we find in high-dimensional data. If the manifold is well constructed, off-manifold is where we might hope to find new science. So many researchers are currently just intuitively combining different anomaly detection techniques, but we hope by viewing the problem explicitly from the perspective of the manifold, it will inform their choices and enhance anomaly detection. It's very much live research, so I'm going to actually apply this to a big sort of DESI data set, hopefully later on in the summer or the autumn. And the idea also is that, and I think this is one of the things with anomaly detection generally, that these techniques are portable to different domains as well. So we could easily use this in medicine, we could use it in financial fraud detection, whatever. And we've got a paper coming out later on in the autumn. So I'll just leave you with a thank you slide. Oh, I think I've missed somebody off. There we go. And just to say, yeah, thank you so much. And I hope if it's inspired any of you to do some anomaly detection, then the more people we've got looking for things, the more chance we've got of finding some interesting stuff. So thank you very much.
Amazing. Thank you so much, Paul, for finding Pegasus.